Hi everyone, my name is Jean-Claude Borel, and in today's e-learning session we are going to discuss how to set up a nonlinear analysis in Diana, and we will also discuss some of the various options that distinguish Diana as the best amongst normal solution. As usual, we will start with a presentation to give you some insight on these nonlinear techniques, and during the live demo we will apply some of this technique to a simple case. So let's start with the presentation. And of course, the first question to answer is why and when should we bother with nonlinear analysis? The general answer to this question is always use a linear analysis, except when there is a good reason for nonlinear analysis. Indeed, performing a linear analysis is much easier than performing a nonlinear analysis. A linear analysis has many advantages. A simple direct solution may be obtained with no need for costly load incrementation and iterative schemes. The superposition principle can be applied. Solution for various load cases may be superimposed. And few material constants are required. The number of material constants required to describe a constitutive behavior is kept to a minimum in a linear analysis. However, there are situations where nonlinear effects must be incorporated for realistic assessment of the structural response. For instance, in the design for both ultimate limit state or serviceability limit state. In failure mode analysis, when you need to detect a failure mechanism or the evolution of existing structures, in forensic analysis or production process analysis, such simulation of material processing or manufacturing, and of course in some research project. Performing nonlinear analysis means that the principle of superposition can no longer be applied. This, for example, the result of several load cases cannot be scaled, factored, or combined as it is done with linear analysis. Only one load case can be handled at a time. Loading history may be important. For example, the nonlinear behavior of a vessel, which is first heated and then pressurized, is quite different if the loading sequence is reversed. The structural response can be markedly non-proportional to the applied loading, and also initial state of stress may be important. In terms of nonlinearities, in general, we might classify them as follows. The physical nonlinear analysis, such plasticity or cracking, geometrical nonlinear analysis, such a large deformation. That would be the case of our demo today. But it can also be nonlinear boundary conditions, like we have in content analysis, for instance. So when it comes to nonlinear finite elements, a general recipe could be first to pick the phenomena to simulate. Then you create your geometry mesh. You choose your material description, so you need to assess material parameters, use a consistent set of units, set properly your boundary conditions, then run your analysis, and finally inspect the results. And this is one of the key. And for the analysis strategies, the main message should be keep it simple. Do not activate all the advanced nonlinear analysis settings in one go. Most of the time, the default parameters are good enough. Always check your model by running a linear analysis first, checking the material behavior and the boundary condition, and also the loads. I mean, quite often you see that loads have been applied in the wrong direction, or boundary conditions are not set up properly, and this can easily be found out just by running a linear analysis. And the final step, explain your results. To a colleague, for instance, you should be able to explain the obtained results and give the good explanation. So your engineering judgment is the key of the analysis at the end, because it doesn't matter which parameter you input, most of the time you get output, but does this output make sense? This is really your judgment, your engineering judgment, that is the key. Generally speaking, the nonlinear problem consists in finding a displacement delta U, but a step in Diana, such that we have an equilibrium between the external and internal forces. And this is usually solved in an iterative way. The general procedure is the same for all iteration processes. In all processes, the displacement increment is adapted iteratively, and that's what we call the incremental iterative solution procedure. In Diana, we have a couple of methods available, such as regular or full Newton-Raphson, where the tangent stiffness matrix is derived for every iteration. We have the modified Newton-Raphson, which differ by the fact that the tangent stiffness matrix is derived for every increment and not per iteration. The linear stiffness iteration method, where in that case, linear elastic stiffness matrix is used for every increment and iteration. There is also the constant stiffness method, which uses the stiffness matrix left behind by the previous increment. This means that if a Newton-Raphson iteration are used during the first phase of an analysis, for instance, and constant stiffness iterations in a second phase, the stiffness in the latter will be equal to the last calculated stiffness in the first phase. If the constant stiffness iteration is used since the first increment, this method is basically the same as the linear stiffness method. The constant stiffness method can be used if Newton-Raphson or quasi-Newton method fails after a certain number of increments. The quasi-Newton method, also called the second method, essentially use information of previous solution vectors and out of balance force vector during the increment to achieve a better approximation. Unlike regular Newton-Raphson, the quasi-Newton method does not set up a completely new stiffness matrix for every iteration. If a deformation process is relatively continuous, then the displacement of the previous increment can be used as a first prediction for the current increment. The displacements are scaled by the ratio between the current and the previous loading factor, or by the ratio of time increments in case of time stepping. If the equilibrium path shows irregularities, it's not advisable to use the continuation method. An irregularity occurs, for instance, at loading and loading points. In that case, the displacement increment of the previous steps are not a good prediction for the increment in the current step. So, having said that, in general, over stiffness matrices lead to a slow convergence, but they are stable. Exact tangent stiffnesses will lead to a fast convergence, but might become unstable. And matrices which are too soft lead to divergence. So these are, attention points. And when you compare this incremental iterative method, you can draw the following trend. And make the distinction between what's more stable and what is a less iterative procedure. For instance, if you compare the different methods, you see that the linear stiffness method is much more stable than the regular Newton-Raphson, but it's require more iteration, and iteration are faster because there's less effort in setup and decomposition of the tangent matrix. So it means that regular Newton-Raphson will be faster for the calculation. So it's always a matter of balance and the type of nonlinear problem that you are trying to deal with. In combination with this incremental iterative procedures, it is also important to choose a reasonable convergence criteria. These criteria are important in the sense that when to reach convergence, you need to reach the criteria that you have specified. If your analysis is load control, then a displacement or energy criteria should be satisfied. If your analysis is displacement control, so you have prescribed displacement, then force or energy-based criteria should be satisfied. On the next slide, you have a summary of the option you can choose in Diana during the setup of your analysis. Under the equilibrium iteration menu, you can find the different method, as I mentioned, the Newton-Raphson, constant stiffness, linear stiffness, and the second. And for the first tangent, you can choose between linear, previous iteration, and tangential. And the different convergence norm that I also mentioned, so energy, displacement, and force. And you can also ask to satisfy all the norm for every step, which is really a tight criteria. And for every convergence norm, you can set up your own convergence tolerance, and you can also you have also the option to continue if the convergence is not achieved. As I mentioned, in 90% of the case, the default settings are good, so don't try to activate too many exotic parameters at the same time. All iteration methods described so far are based on a, let's say, reasonable prediction, so that the iteration process converges to the exact numerical solution. If the prediction is too far from equilibrium, the iteration process will not converge. This easily takes place in structure with strong nonlinearities, for instance, when you have cracking. In that case, line search algorithm can increase the convergence rate and are especially useful if the ordinary iteration process fails. So this is one of the options you can activate. And to activate this line search option, you also do that from this iterative method dialog box by activating the line search, and here you can define all the settings. For more detailed information about all these parameters, I invite you to refer to our online documentation where all these parameters and theory are discussed in detail. In ordinary iteration process, the predictions for the displacement increments can become very large. This is the case especially if the load displacement curve is almost horizontal when you reach top. If a fixed load increment is prescribed, this results in very large predictions for the displacements. The problem can be overcome with the use of arc length method. Using the arc length method, snap-through behavior or snapback behavior, like depicted on the two pictures A and B, can be analyzed. So this can be a very powerful tool. And again, to activate this arc length control, you do that from the load, the execution of the load step window by checking on the arc length control and by clicking on the settings, you have access to more settings and also to the control sets for your selection. And we will use this method in our case later today. So to conclude this presentation, based on experience, we can draw the following guidelines. Carefully pick your convergence norms. A tight criteria requires many iteration, where loose criteria may cause problem in next step. But if you are to lose, I mean, your load displacement curve can take a completely different path, which is absolutely unrealistic. And if it's too tight, basically you won't be able to find a solution. So again, you have to find the right balance. As I mentioned already 2 times in this presentation, do not start with too many exotic solution features. Using default setting is enough in most of the cases. And in Diana, we have predefined settings that are robust and can, in most of the case, do the job. Line search algorithms are especially useful if the ordinary iteration process fails. And for force control softening or snap through problems, use arc length method. These are some guidelines that you can use when you have to perform a nonlinear analysis. And if you want to know more about all this iterative method, you can always refer to our online documentation where all the theory is described in detail. And we have also a good number of tutorials who are using this nonlinear approach. So having said that, let's move to the demo of today. We are going to study the behavior of inch plate panel subjected to a point load in the center. Due to the symmetry of the model, we are just going to model 1/4, the one quarter of the geometry, the one depicted in gray. During the live demo, we will highlight the advantages of choosing a proper nonlinear iterative scheme in conjunction with advanced technique like arc length and their corresponding settings to obtain a solution for a highly nonlinear model. Material and geometry is a property of the model are listed in the 2 tables. So material is linear, and here are the different length and radius and thickness of the panel. The model will be simulated with curved shell elements, and the following boundary condition will be considered, so that we have 2 symmetry planes that we'll consider, and we will fix the displacement in x, y, and z direction at the edge at theta 0.1 to simulate the inch connection. So having said that, let's move to Diana. Here we go. So as you probably know by now, the first thing we need to do is to set up a new model. And we do that by starting a new project. So file new. I'm going to call it demo inched panel, for instance. I'm going to browse to my working directory. So for the analysis type, I choose structural. It will be a 3D model. I'm going to use a model size of 100 meters. So you by now you probably know the meaning of this model size. Huh? It's the dimension of the modeling box. So if your model is too big, you have to increase this model size. So you should make sure that the size of your model can be fit in this box. For the default measure type, I go for exact quad dominant, and I go for quadratic order and on shape. In terms of units, I'm going to set up the model in millimeter. For the mass, I choose ton, Newton, second, Kelvin, and radian. So we are all good. I'm going to build the geometry. And as you could see in the presentation, the geometry is relatively simple. So it's I'm just going to model an arc and extrude this arc to get the quarter of the panel I want to model. So first I define the arc, for which the radius is 2556 with a starting angle of 0.4708 radian and 0.1. I click create, I fit all. So due to the large radius, you hardly see any curvature, and my arc appears under my shape. So next, I'm going to extrude this arc. So I select it, and I'm going to extrude it in the Z direction by 254 millimeter. If I do fit all and apply, here is our model. So basically it's 1/4 of the geometry. Next, I'm going to already assign the property. You will see that for the modeling part, it's very simple today. The main focus would be on the analysis part. So I'm going to assign some property to the model. I select my geometry. I choose for regular curve shells, and I'm going to define the material that I call steel, for instance. Keep it linear elastic. I put Young's modulus. Okay. Then I need to define also the thickness. So I call it panel, and the thickness for this one is 6.35 millimeter. Click OK, and then apply. So under material, I have my material. I can choose to make a different color and show by assignment. And you see that the material is properly assigned to the geometry. Next, we are going to define the boundary condition. We have 3 sets of boundary conditions to define, 2 symmetry condition and each condition. So I start with the inch. I select edge, and I select this edge, for which I constrain the 3 translation. Create. Then we go for the X symmetry, sim X. Select this edge, and in this one, the X translation is fixed, and I constrain the rotation around the Y and Z axis. And finally, I have the symmetry Z. for this one, I'm going to constrain the Z direction in terms of translation and the rotation on the X and Y axis. And I create. So we have created our three boundary conditions. We have assigned the property. The last thing to do is to apply this point load. So I'm going to create this load. Point load. To a vertex, it's a force, and I'm going to apply it on this node here. And the force we want to apply is 1000 Newton, but since I just model 1/4, I'm going to apply 1/4 of this value. So 250 Newton, acting along the Y direction, but downwards, so minus 250 Newton. In Y. And I click create. So now if I look under the geometry tree, I have my three supports and I have my load case. So the model is almost finished. The last step is to mesh it. So for this model, we are going to use 6 division. And I click on mesh. So our model is ready, and now let's move to the attention point of today, the nonlinear analysis. So I go to analysis. I can rename it to nonlinear. And I'm going to use structural nonlinear analysis. If I edit the nonlinear effect, I can see the nonlinear effect that I can consider. And in this nonlinear analysis, I'm going to consider the geometrically nonlinear effect. My material is linear. Then I'm going to apply my load, which will be the point load, and I'm going to apply it in increment step. And to do that, I'm going to define a size of 0.01. So it means that every time I apply 1% of the prescribed force, and I'm going to repeat this 75 steps. So it means that if the analysis goes until the end, 75% of the total load will be applied. Then if we look at the equilibrium iteration process, so this screenshot that I was showing in my presentation, I'm going to use the default method, the Newton-Raphson, with the first tangent as tangential. I'm not activating line search or any continuation things. And I'm just going to increase the maximum number of iterations to 30. Let's say that when it comes to number of iterations, 30 is a good number. If your analysis do not converge within 30 to 50 iterations, most of the time you have to look a little bit further to see if there is any problem. Increasing the number of iterations most of the time doesn't solve it. So let's start with 30 iterations. And for the convergence norm, I'm going to check the displacement and force norm. And I'm going to make the criteria a little bit tighter than the default one. I'm going to use 1e-5. So I make it much tighter. And here we go. So I'm going to perform this analysis. And you can see in the message box that you have information about the steps, how far are you in the analysis, and the convergence. And what I see here, it's that the last step down, step 59, didn't reach the convergence. You can see that the displacement variation and the outer bound force didn't reach the criteria. Where if I go back to the last converge steps, I have to scroll up a little bit. You see that for the force, I got convergence. So one of my criteria was fulfilled, and the convergence was achieved in 4 iterations. So this is good habit to check the information that is provided in the message box, because it gives you a good information about the convergence of the different steps and how fast was reached the convergence within this step. So having said that, we are now going to look at the results, and I'm going to plot the force displacement curve, which will show how far we went with this analysis. So I'm going first to present the Y displacement, and I'm going to select the node here. That's the node where we have applied the force, and I'm going to plot the force displacement diagram here at this point. So I'm going to select this node here, and I say show table, and I can see that my load displacement curve is nonlinear and reach a peak here. And here you see that this is the last step, which is not converged. So this result is not really reliable. So the last converged step is here. So it reads that it's clear that when you look at the profile of the curve, you are reaching a kind of a top here, and we cannot go further with the current setting of our analysis. So in that case, and because this nonlinear problem, we know that we should expect a certain behavior. We are going to use and activate the arc length method to see if we can capture this snapback behavior. So what I'm going to do, I'm going to duplicate my analysis. And this one, I'm going to call it nonlinear arc length, for instance. And in terms of settings, I'm going to edit the load settings by activating the arc length control. And I'm also going to increase the size of my step, where now I apply 10% at every steps. Yeah, one less. So every step I apply 10% of my load, and I'm going to activate the arc length control to see if I can capture this snapback behavior. And I'm going to define a control set where I include all the node numbers, and I'm going to do that on the Y displacement. So this is the only thing I have to do. I activate this arc length behavior, arc length method, and now I rerun my analysis. So this one takes a little bit more time. I have already the analysis performed. I can go back to the message box. So what happened after running the nonlinear analysis, but with arc length method? You see now that I have 75 steps. They are all converged, and in terms of loading factor, I went much further than the previous analysis. So let's see what it means. So if I look at the result of the nonlinear analysis with arc length method, So again, I'm going to look at the Y displacement, and I'm going to present the load displacement curve. So again, I select the node here, and I show the table. You see that we can capture this snapback behavior, snap-through behavior. In the previous analysis, the curve was reaching this point, and then we were reaching divergence. But by activating the arc length method, we could go further and capture this snap-through buckling behavior. So this is one of the powerful tool that you can use when you have to capture such a behavior, is to activate the arc length method. So this is it for the presentation of today regarding this nonlinear iterative procedure and tools. What we learn is that a nonlinear method, a nonlinear analysis is more complex than a linear one, of course. You have more settings to take into account, but always try to keep things simple and don't activate all the exotic features that Diana may offer in one go. Always be critical about your results, because you can always have a set of input. In most of the case, you will get output, but does your output make sense? This is based on your engineering judgment. And the last thing I wanted to say is in most of the cases, running a linear analysis may save you a lot of times later on, because you can identify problems such as wrong boundary condition, wrong loading, or wrong material that may be difficult to find out once you have activated a nonlinear analysis. So these are some guidelines. The best thing is experience. So the more you run this type of analysis, the more familiar you get with all these parameters and the criteria. So you need to always to build some experience. You can use most of our tutorial. We have a good number of them who are using a nonlinear analysis, and it covers different aspects and different iterative methods. So they are good tools to practice and to get familiar with these methods. And again, if you want to dive into the theory of all these methods, if it's of interest for you and you want to get a better understanding, you can, of course, refer to our online documentation where the theory is fully described. So this is it for today. I want to thank you for attending this webinar. Thank you. Bye.